So I'm Matthew Treinish, and I'm going to be talking today about Qiskit's transpiler. Before we get started, here is a code assistant prompt. It generates valid code. I don't really have much else to say about it. So before we get started, here's a brief agenda of what we're going to be talking about today. I'm going to start by talking for hopefully about 60 minutes about how Qiskit's transpiler works, how it's architected, and how the presets are all built. Then we're going to go into about 20 minutes on the transpiler service from David. Then Peter is going to talk about error suppression in Qiskit runtime. And finally, Elena is going to follow it all up and put it all together with a comparison of all of these tools and why you would use them. So to start, we'll get into the details of the transpiler. So before I dive into it, I did want to make a quick note on terminology. This sometimes confuses people. In Qiskit, we call it the transpiler. This is mostly a historical name from like the origins of Qiskit. It doesn't fully represent all of the capabilities we have in Qiskit today. It's often called a quantum circuit compiler as well. I tend to use the terms interchangeably, and some other people on our team do. So if you hear me say a compiler or it compiles, I'm referring to the transpiler in Qiskit. It's the same thing, in this context at least. So to get started, why do we need quantum circuit compilation? If you think about it from programming for a classical computer, we're programming at a pretty low level for quantum computing. We're writing individual operations on individual quantum bits. And if you think about like writing something like Python code, you're not worrying about the individual bits in the microprocessor. You're writing in a higher level language that adds abstraction. But the thing is, when we're building these quantum circuits, there's still a lot of abstraction away from the hardware. And this abstraction needs to be accounted for before we can run it on the hardware. And the compiler's job is to lower that higher level representation to something that's actually executable on the hardware. So to show this, I've put up this Bernstein-Vazirani circuit. It's just a textbook circuit. The details of it don't really matter, except that it has a deterministic result. And for that, it's easy to demonstrate the value of a compiler. So this circuit is very low level, to standard textbook gates, Hadamard, C0, and an X gate, and then some measurements, and the barriers just for visualization in this case. And if we compile it with 3 different settings in Qiskit, we have a terrible compilation where you can't even make out individual gates. And I had to go to some effort to make Qiskit do it that poorly. A good compilation with, actually I think that's with the default settings now in Qiskit 1.3, and then better compilation where I went to some effort to get Qiskit to generate the best circuit I could come up with. But that doesn't mean it's the absolute best. It's the best I could come up with, which is why I called it better. And then if I run these devices on Treinish, which is the target device I compiled for, we can look at the histogram of the results. And as I said, there's a deterministic outcome from the circuit. So there is one right answer. And on the bad compilation, you get random noise. You have no idea what that correct result is. On the good compilation, it's pretty clear. It's that all zeros bit string. And on the better compilation, it's even better. It's almost all of the results. And this shows the value that the compiler can have when you're building your circuit. And the job of the compiler is to try to get you to get that reasonable signal so you can do work with your circuit. And so to start to look at how the compiler works, the first thing we need to look at is what are the constraints of the hardware? What is the compiler actually fitting your abstract representation of the circuit to? And the first one is the easiest one to understand, I feel. And that's the supported operations, the supported gates that the quantum computer supports. So each quantum computer supports different gates that are calibrated and represented, at least on our superconducting quantum bits, as microwave pulses. And they're mapped to these quantum gates. And each quantum computer supports a different set of them. Typically, there's a universal gate set, so it's some gate set that can be used to construct any unitary operation, and you can build out your quantum circuit with these. And so on the right, I've listed what the previous 3 generations of IBM processors supported. So on Heron, we have a CZ gate, an RZ gate, square root of x, x, measure and reset. Eagle, we just replaced the CZ with an ECR. And then Falcon was an interesting one, because Falcon actually supported ECR and CX, depending on which qubits you were using. And that's something that's often not accounted for, that Qiskit can handle, is that all qubits don't need to necessarily support the same operations. And so it's the compiler's job to understand this and make sure that you're translating whatever the input circuit is into what's appropriate for the qubits it's running on. The second constraint is also kind of intuitive when you look at a dye photo. And I wish I had a newer dye photo because this is a really old one that everyone uses in every IBM Quantum presentation I've ever seen. So this is an old 5-qubit dye photo. I think it used to be IBM Yorktown. But we're going to be talking about qubit connectivity. So qubits in a quantum processor have limited connectivity. On IBM superconducting hardware, that's because there's physically a connection between the qubits. So on this dye photo, you can see those squares. Those are the qubits in the photo. And then the Bs represent bus resonators that are between the qubits. And you need one of those to run a 2-qubit operation between those qubits. And so when you're trying to build your circuit, you have no constraints on which qubits you can have connectivity between where you're running operations. But in the actual hardware, there's a limit. And the compiler's job is to understand this and map your circuit accordingly so it's actually executable with these constraints. And with 5 qubits, it's easy. But if you look at Treinich's connectivity graph, so this is just a graph representation of the connectivity on the processor, obviously not a dye photo, it's much harder to reason about. When it's 5 qubits, you could probably map it out by hand and it'd be pretty easy. But at 133, I don't know how much time you have, but I don't have time to sit there drawing it all out. And then the next question from that is, okay, well, what happens if your circuit has too much connectivity and your device can't support that? And so here's just, if we think about that 5-qubit example before, that 5-qubit dye photo, if you had this circuit, there's no connectivity. Let's see if that's back. Yeah. There's no connectivity where there's 2 qubits that are connected to all of the other ones. So there's no way that you could run this circuit as is on that device. And so what the compiler does is it uses swap gates out of the box in Qiskit, although you could use other techniques, to move the quantum state around between the qubits as it's evolving the circuit to make up for that lack of connectivity. But the problem with inserting swap gates or the other techniques is that swap gates are, there's an example of how that circuit would be transformed with swap gates, is that swap gates are expensive from a number of operations. So each swap gate, no matter which architecture you're targeting for, ends up being 3 2-qubit gates, which, when we look at the next constraint, has a significant overhead to the execution. And that next constraint is noise. And this is the biggest one that the quantum circuit compiler has to deal with. No matter what you're doing on a quantum computer, there's a source of noise or error. And so on the right here, this is actually from a paper we published a year or 2 ago, is a distribution of the error rates and coherence times on 3 generations of IBM processors. But you have gate errors, so single qubit gate errors, multi-qubit gate errors. You have decoherence. You can only maintain the quantum state for so long. So you have T1 and T2 times that represent that. And then you also have readout errors, errors when you're taking a measurement. So the measurement might not be the actual state. And so you can see they're also very variable, the error rates between all of these things. And the compiler's job is to try to optimize your circuit, accounting for this noise so that you get the best signal out. And we'll look in some more detail at how Qiskit does this in a little while. And so in Qiskit, all of these constraints are modeled with one object called the target. The target is basically consolidates all of these different constraints and represents all of these aspects in one view, so the transpiler can just query it whenever it needs to know about the constraints for its different processing. So in this case, I actually took that same 5-qubit one because it's easy to visualize, and just printed the target or a subset of it because there's too much detail in there, and I doubt anyone in the back can read it. But all it really does is list out, okay, I support CX between 0 and 1, 1 and 0, 1 and 2, and then the associated error rates and duration for each of those gates. And then also that there's a pulse calibration, but there's no textual representation of a pulse waveform. So it just says there's a pulse calibration for this view of the target. The target also contains additional properties like the coherence time for the qubits that were measured in the last calibration run and other details. But For the most part, we're not going to be looking too much at that in this presentation, but the target is there to represent all of the constraints that a particular quantum computer has that the compiler needs to deal with. And so now that we understand the constraints that the transpiler has to deal with, now we can look at how the transpiler is constructed and architected. And the first thing to understand is the DAG representation. So in Qiskit, we represent a quantum circuit in the transpiler as a directed acyclic graph, or DAG. The DAG tracks the data flow of quantum bits, classical bits, and then also classical variables from the start of the circuit to the end of the circuit. So if you look, let's see, laser pointer. Nope. No one can see it. OK. So if you look at the DAG representation on the right, there are the green nodes, which represent the input nodes, or the state at the start of the circuit. And you can track the flow of the bits through the blue nodes, which represent operations, to the output, which is the red node. And what this lets us do is efficiently analyze the circuit for different ways. Knowing the data dependency lets us realize certain characteristics of different operations more easily. We'll look at, it's a bit hard to describe in words, but we'll look at some concrete examples in a little bit. The easiest one, I think, to think about is in-place substitution. If you want to replace one node with an equivalent operation, this lets you very easily do it because you know exactly where the dependencies are between all of them. So for example, if we wanted to take that excitation preserving block and replace it with a sub-circuit that was smaller operations but equivalent, the DAG representation makes it very easy to insert the operations in the correct place. And in Qiskit 1.3, which recently had its release candidate last week, so you can install it today, the DAG circuit is now all in Rust. In previous releases, it was using a library called RustWorkX to represent the graph, which was in Rust, but it was a Python object. And in 1.3, for performance, now the entire object is in Rust, which really opened up a lot of performance opportunities. And so once we have a DAG representation of our circuit, the transpiler is broken up into 3 levels of hierarchy. The lowest one is a pass. And a pass is, you could think of it like a function, really. It's a very simple operation on that DAG. It either analyzes it or transforms it. And you execute these in series to perform one job. So for example, you have a pass that just unrolls a gate. So if you have like a big compound operation that's represented with a node, you could have one pass that just takes that and unrolls it. You can have another pass that cancels redundant gates, so it finds redundancies. You have one that maps it. And you have all of these passes, and you write these in isolation to do one job. It kind of follows the old Unix philosophy. Do one thing and do it well. These passes are then aggregated into a pass manager. Pass manager is basically an execution pipeline. It lets you execute sequences of passes with control flow. So you can have if-else statements, for loops, while loops. And it lets you control the execution of these passes so you can orchestrate them to perform some goal. And the other aspect of a pass manager is that there is a property set, which is a global metadata store so that you can pass information between passes. So a common pattern is you have an analysis pass that will look at the DAG circuit, compute some attribute of that DAG circuit, and then that will be used to inform a control flow branch later in the pass manager. And so you can store anything from a pass on the property set and then use that in a later stage of the pass manager to do something with it. And then each of those pass managers becomes a stage in what we call a staged pass manager. And this is the highest level of the hierarchy. So the stages are basically assigned semantics to a pass manager that you execute sequentially. So in Qiskit's preset pass managers, the defaults that when you run generate preset pass manager or the transpile function, has 6 stages, which init, layout, routing, translation, optimization, and scheduling. But in the hierarchy of Qiskit's transpiler architecture, these are just what we pick by default. If you're building your own pass managers, you can define whatever stages you want. and assign whatever semantics you want to them via a name. That's all it lets you do. But you define the stages, and these are all executed sequentially, but inside each one of these stages is a pass manager which has that control flow and may have loops, may have branches, whatever. But each one of these executes sequentially. And so for Qiskit's transpiler, what this means is that we have the sequential lowering and optimization to something that is then executable on hardware on the output. And to just quickly go through these stages, we'll be walking through the preset pass managers and what each of these stages do in some depth. But I think it's useful to go through each of the 6 stages and understand what they do. So we have the init stage, which is designed for any initial transformations that we need to do to the circuit. And that includes setting the stage for the next one, which is layout, which is used for mapping the circuit qubits to qubits on the device. Then we have the routing stage, which inserts those swap gates we talked about earlier to account for a lack of connectivity on the device that's necessary to run the circuit. Then we have the translation stage, which translates all of the operations in the circuit to something that's supported by the device. The optimization stage then takes all of that work we just did and tries to optimize it as much as possible. And then the scheduling stage is the last stage that tries to account for the timing of the circuit so that you have an understanding of how long each of the operations will take when you execute the circuit on hardware. And the other thing that's important to talk about with the pass manager and the staged pass manager in particular is its pluggability. So this entire architecture is designed to be modular and extensible. And so what this lets you do is you can just generate a preset pass manager or generate a staged pass manager and modify it. Add passes to a stage, change an entire stage, however you feel is necessary to alter the compilation for your specific workload or your specific target device. And then built on top of this extensibility, there's also a plugin manager that lets people build plugin packages that are Python packages that can extend the functionality of Qiskit's transpiler so that you can run bespoke optimizations or things that are not maybe general purpose, but for certain applications have a clear advantage. And it's also really good for experimentation. So if you're working on a compiler technique, you can publish a package that lets anyone experiment with it. And for a concrete example of this is something I worked on with interns last year, is this Qiskit qubit reuse plugin. So this is based on a paper from Quantinium, where they published a technique for doing qubit reuse through mid-circuit measurement using dynamic circuits, where you can take a circuit and reduce the number of qubits you need by reusing it and doing a mid-circuit measurement and resetting it. So if we look at the same Bernstein-Vazirani circuit that we looked at in the very first slide, we install this qubit reuse plugin, and we just specify for the init stage, use the reuse plugin, don't use the default stage. It generates a pass manager that uses this external package. And then when we get the output, you can see we reduce the width of the circuit from 4 qubits to 2, because in this case, that pass is able to optimize it. But this technique is not general purpose. It only works in very specific cases. And in those cases, there's always a trade-off between reducing the width and then the extra measurements that you have to do, which introduce a certain amount of error. So it's not a general purpose solution, but in a Bernstein-Vazirani circuit, it actually makes it much better. For other circuits, not so much. I use this plugin for the better option when I was looking at the 3 compilation options before. So now that we've covered the architecture of Qiskit's transpiler, now let's look at how the preset pass managers are actually constructed and how they work, and how all of the passes on the inside of the transpiler work. So I'm going to be looking at optimization level 2 and using Qiskit 1.30 RC1, the most recent, well, pre-release. The final release will be next week, but you can pip install that today and experiment with it. We're going to be going through each of the stages and looking at the passes that are run and how the pass managers are constructed to get a feel for how Qiskit is transforming your circuits as you run the transpiler. So the first stage is the init stage. The init stage is divided into 2 phases. The first phase is to decompose larger gates or operations that are 3 or more qubits into 1 or 2 qubits. And this is primarily to enable layout. So all of the layout algorithms that Qiskit runs today do that by representing the circuit as a graph. And you can't have more than 3 qubit gates in a graph representation. That would be a hypergraph, and that wouldn't work. So the init stage is designed to lower all of those multi-qubit operations to 1 and 2 qubit gates so that we can then put it on a graph to run our layout algorithms. The other thing it does is logical optimizations. So at this point in the transpiler, we still have an abstract circuit, and we don't know which physical qubits we're on. We don't know the constraints of those qubits because the operations could be different depending on the qubits. But there are some optimization techniques that are independent of what those constraints are, and we can run those ahead of time to simplify the circuit early and then make the rest of the transpiler's job simpler. And so if you look at the representation as like a control flow graph of how the pass manager is built, or how the pass manager for the init stage is built, we have this clear dividing line where the top are the decomposed larger gate stages, and this is actually the translation stage. These are the same passes, so I'm not going to talk about them here. We'll talk about them during the translation stage. But the constraint on these is they only run for 3 or more qubit operations. And if it's 1 or 2 qubits, we don't touch it yet. And then we have the logical optimization stage here, and that's all the passes, the bulk of the work runs underneath that purple line. And so what this does when we run the init stage is if we're going to be looking at the same circuit, the excitation preserving block with these controlled RY gates in the beginning. And if we run the init stage, we go from this circuit to that circuit. And you can see the most obvious thing here is that that block is gone, and now we have 1 and 2 qubit gates. That's basically the job of init. But the other thing that's a little bit harder to see is that there are some gates that have been removed. Some of the gates have been removed from what that definition of that exciting preserving block is. Some people who are familiar with it might be able to see what's missing. But the most obvious one is that RY of 0 is removed. And that's because one of the optimization passes realized that doesn't have any effect on the circuit, and we can just remove it. And so to look at the logical optimization passes we run in the init stage, I'll go through some of them. Actually, all of them, all but one here. So the first one is the remove identity equivalent pass. And that was the one I was talking about. This just looks at every operation in the circuit and determines if it's equivalent to an identity gate, which means it has no effect on the state of the circuit, and it just removes it for efficiency. Then there's a remove diagonal before measure pass, which similarly looks for a diagonal gate that's right before a measurement. And because the diagonal gate wouldn't affect the output of the outcome of a measurement, we can remove that operation and just save an operation. So this just looks for measurements and then looks at the immediately preceding gate and checks if it's a diagonal. And if it's a diagonal, we can remove it. Then there's the inverse cancellation pass, which just looks for adjacent or pairs of operations that are inverses of each other. So CX gate is a very good example of this. If you have 2 CX gates next to each other, they're self-inverse, and you can just remove those. But you can also do this with all sorts of other pairs of operations like S and S stagger. Then there's commutative cancellation, which is removing inverse pairs, accounting for commutation relationships between gates. We'll cover that in more depth because we also run that in the optimization stage. So we'll talk about that in a little bit more depth later. Similarly, consolidate blocks is a pass that's used to consolidate operations into blocks of unitary matrices. We'll also talk about that during the optimization stage because we do that there as well. And then the final pass on this list that we'll talk about is split 2 qubit unitaries, which looks at any unitary gate, which is a gate represented solely by its matrix, to determine if it's actually a unitary that's defined as a product of 2 single qubit gates. And if that's so, it'll decompose it into 2 single qubit unitaries instead of 1 2 qubit unitary. That's pretty uncommon, but sometimes it comes out of consolidate blocks that this happens, and this can lead to efficiencies in later stages. And the other pass we run in the init stage that I thought warranted an example, all of those other ones are pretty self-explanatory, but this one I thought is useful to explain, is the allied permutations pass. So in the init stage, we haven't picked physical qubits yet. But if there are any permutations in the circuit, like a swap gate, or there's also something called a permutation gate, which is just like a swap network, we don't actually need to execute those swaps because we haven't picked physical qubits. We can simply swap the virtual qubits in the circuit and have the same effect as what running a swap gate would be, but we can do it ideally because there's no actual physical gate that we're running. So in this example here, I just put together a quick circuit that had 2 swap gates in it. And if we ran allied permutations, all it does is it goes through the circuit in order. And when there's a swap, it just swaps the qubits in the circuit so that everything that was on one qubit is now on the other. So for example, as we go through the circuit on the top, we go through the Hadamard, then there's a swap. So then qubit 0 becomes qubit 2. So everything that's on qubit 2 after that point in the circuit now moves to qubit 0. And you go through the circuit in this order. And then what the transpiler does is on the property set, it tracks what the permutation that's caused by doing that is, so that we can then return that to the user, and then things that need to know about the permutation, like an observable for the estimator, can account for it. And so you can see here we're able to eliminate 2 swaps by running this pass. This optimization is only valid in the init stage because as soon as you pick physical qubits, then you can't just swap physical qubits virtually because they're in hardware like we looked at. So we can only run this during the init stage. And so coming out of the init stage, we go into the layout stage. And this one is deceptively important. It impacts more than I thought intuitively when I first started working on the transpiler. And so we go to a lot of computational effort here because its impacts are pretty severe on the outcome of executing the circuit on hardware. So the layout stage's job is to take those virtual qubits that we were talking about before and map them to physical qubits on the QPU. And the reason this is so important is twofold. The first is, as we looked at when we were talking about noise, no qubits are the same. The error rates are very different between them. And so you want to try to pick the best performing qubits so your circuit performs the best and has the least amount of error when you run it. But then also picking a bad layout can induce a lot of swaps. So if you pick qubits that are on opposite ends of the chip, but there are a lot of operations between them, you'll have to swap a lot to get those operations to run. And the more swaps that you induce, each time you add a swap, that's 3 2-qubit gates, which adds a lot of potential error to your circuit, and you want to try to minimize that. So the worst example in that first Bernstein-Vazirani example, what I did to make it that bad was I told the transpiler, move the qubits on opposite ends of the chip, make them go as far away as possible. And then that's why you had that nice wave, because it kept swapping between them to do the operations. And so you want, the transpiler is trying to pick the best qubits, accounting for noise, and trying to reduce the amount of swaps. So because we go to some effort, we run 2 passes to try to do layout, VF2 layout and Sabre. And when we run this stage, you can see how the circuit is transformed. The actual operations don't change that much, but the biggest thing is here on the left, we have qubit 0, 1, 2, and 3 in the beginning of the stage, and at the end, they're mapped to physical qubits on the device. So we have qubit 2 that goes to 83, qubit 0 that goes to 84, qubit 3 that goes to 85, and so on. And that's basically what the layout stage's job is. Also, eagle-eyed people will notice that there are 2 swap gates here. We'll talk about that in a second. Also, an internal barrier, but you don't have to worry about that. That gets removed later. So let's look at these 2 passes that we run. The first is the VF2 layout pass. And the VF2 layout pass builds a graph representation of all of those 2-qubit interactions that you had in the circuit. So it looks at the circuit and basically builds a graph if there's like a 2-qubit gate between any 2 qubits. So if we look at that excitation preserving block before, that circuit after we did the decomposition in the init stage, we end up with a graph that looks like that. And this pass is just looking for an isomorphic subgraph in the target's connectivity graph. Those are really fancy words to say, can we map that graph to something on the graph on the right? And in this specific example, by human intuition, we can clearly look at these two pictures and say there's no way to map them. But this is a very simple example. For more complicated circuits and more complicated devices, this is intractably hard. It's actually an NP-hard problem to do this. And so in Qiskit, we used the RustWorkX library and its VF2 algorithm implementation to solve this problem. We've added some heuristics to RustWorkX that make it particularly well suited for solving it with the constraints of quantum computing. But it's still an NP-hard problem, and sometimes this can take a really long time. So what Qiskit does is also put bounds on the search space so that it can only take a certain number or a certain amount of search steps, which cap the amount of time that you can spend looking for one of these. In this case, it would return almost instantly because there's no mapping here. But for more complicated problems, it can take a really long time. And so that's actually one of the knobs we turn as you increase optimization level. So if you were to run with optimization level 1, the search space is constrained even more. And if you run optimization level 3, it's opened up, so you spend more time. And because if you can find a perfect layout where you can map this exactly, then you don't need swap gates. And that's the best case scenario here, because then you don't need a single swap to run your circuit. The other thing this pass will do is if it finds a mapping, there might be other ones out there. And so it tries to find all of the mappings it can within that time budget. And then it looks at the error rates in the target and tries to pick the best qubits. So that you run on the best set of qubits with the best mapping that will perform your circuit the best. And it will do that up until the search space limits or until it can't find any more subgraphs. But since, as in this example, there's not a guarantee that there's a perfect layout, a layout where you don't need swaps, then we need a pass that runs when you need swaps. And so that's where we run this pass called Sabre layout. Sabre layout is based on this paper from a few years ago called Sabre. And how this works is it starts with an initial random guess, and then it runs a routing algorithm that would be used to figure out how to insert swaps. But instead of inserting a physical swap in the circuit, what it does is it swaps that mapping. It swaps the qubits in that mapping, kind of like how Allied permutations works. And then it goes forward and backwards over the circuit. So it'll iterate through the circuit, and every time it determines that it needs to insert a swap, it'll swap it virtually, and then it reaches the end of the circuit. Then it reverses all of the edges in that DAG representation and works backwards. And the goal of this is to try to converge the qubits where you have the highest degree of connectivity so that all of the operations that need to work more closely together do. And we repeat this going back and forth multiple times and hopefully converge on a good solution. And so I have an animation showing how this works. So you can see here, the red it's evaluating a swap as it's iterating through the circuit. And then the green represents it has swapped the qubits virtually, and the indices change as it determines that it needs to make a swap. So the red is every possible swap that it's evaluating. And it goes through this and until it reaches the end of its search, and hopefully this new layout is better. But because this is so expensive, one of the things we've done in Qiskit is build on that original Sabre paper. And so recently we published a draft paper on arXiv called Lightsaber, which is our improvement to Sabre. And one of the things that we demonstrated in that is that we're able to run this in parallel. Because we start with an initial random guess, that random guess can actually strongly influence the output result. So whenever you run the Sabre pass, it's actually running in multiple threads, 20 random guesses at optimization level 2, and it's running the same algorithm, and it's picking the one that results in the fewest swap gates. And so that's what's running here. It's the same algorithm, but with 20 different random starting points, and no one can see the indices, but they're all different, and it will just pick the one that resulted in the fewest swaps at the end. Yeah, so that's basically an overview of Sabre, which leads us into the routing stage. So at the end of the layout stage, we've picked our physical qubits, but now we need to insert swaps. The default pass for this is actually Sabre swap, where we run the same routing algorithm with the same heuristics that we did for Sabre layout, but instead of mapping the qubits virtually to pick a layout, we insert physical swap gates. But in the preset pass managers for Qiskit, for efficiency, we actually do that as part of Sabre layout. So it's really a lot faster to just, as we're going back and forth at the very end, instead of doing it virtually, you just insert physical swaps. And so that ends up saving a lot of runtime as an optimization. But because everything is pluggable and modular, someone could change the layout stage so Sabre doesn't run, or change it to be a pure layout pass that just does the mapping. And so because of that, we run Sabre swap in a conditional block, so that if it's not already mapped, you run Sabre swap and run that algorithm by default. But in the preset pass managers, we skip it because we've already inserted the swap. And so that's why at the end of the layout stage, you could see there were swap gates in there already. And this is just a runtime efficiency thing. It's the same algorithm, just split out. But ironically, the thing we do run in the routing stage is a layout pass. So we run this algorithm VF2 post layout, which is after we've inserted swaps, to run an additional layout algorithm to try to optimize it even more. And so let's take a look at what the VF2 post layout pass does. So the VF2 post layout pass is basically the same algorithm as VF2 layout, except when you run it after routing, you're guaranteed to have at least one isomorphic subgraph. That's the goal of the routing stage. You're transforming the circuit connectivity to map to the device. So you know that there's at least one there, but there could be others. And that RustWorkX algorithm that we talked about before with all of the heuristics that we've put in that make it well suited for this problem can find those very quickly because it's well aligned to the structure of the connectivity graph. So if we look at the same problem before where we have the interaction graph that we generated from the circuit and the connectivity graph of the device, you can see that there's clearly a mapping there and more than one. And so the VF2 post layout algorithm is trying to find the one that has the best predicted fidelity. So it looks at the error rates of all of the operations on all of the qubits and picks the best one that would result in the lowest error based on the reported error rates of the device. And so we can see this in practice. So this is going to be a visualization, and you can see the green is the numbers represent the current layout. Red is a potential subgraph that it's evaluating. That went faster than I thought. Let me try this again. And it's trying multiple layouts with red, and then it settles on green as the end choice. And you can see at the end, it's picked those middle qubits because those had the best error rate in the target that I ran this, or that I generated this visualization from. And so for this one, it's pretty simple because it's a pretty small graph. But for more complicated examples, obviously, this problem can be much harder to solve. But so then at the end of the routing stage, what we have is a circuit that is matching the connectivity constraints of the device, and it's picked the qubits with the best predicted fidelity. Which leads us into the translation stage. So now that we've picked our physical qubits, we can look at the target and figure out which operations are supported on all of those qubits we're running on. And then we need to translate the operations of the circuit into the operations supported on those qubits. And we run these three passes here, which are the same passes that we ran in the init stage for that initial decomposition of multi-qubit gates. Except now we run them on all gates, and before we only ran it if it was 3 or more. So the first two passes are high-level synthesis, which Julian was talking about yesterday, and then unitary synthesis. And these are pluggable passes. So these are designed if you have any higher level, more abstract operations that are defined by some mathematical operator. Unitary synthesis is much easier to think about because it's a gate that's represented solely by its unitary matrix. And this pass is designed to synthesize just those. And it's pluggable so that people can come up with a new technique to go from a unitary matrix to a circuit and then write a plugin specifically to do that. So you can write a plugin that just does that. We give the plugin a unitary matrix, it returns a circuit. And Qiskit has 3 built-in plugins for this. One that does approximation that I believe Ali will be talking about in the second half, or the second seminar today. The high-level synthesis pass is basically a generalization of that. It says that you can write a plugin to synthesize any higher-level object, and it will look through the DAG and see if there are any plugins installed for any gates, and if there are, it will pick the one that's specified to run, and then we'll synthesize that. And so built into Qiskit, we have plugins for a lot of these higher-level gates, like a Clifford, so you can just put a Clifford tableau directly on your circuit, and this pass will see that and synthesize it. But then also polyevolution gate for the evolution of a Hamiltonian that Julian was talking about yesterday. That is another example, and the list goes on. But this is also open, so anyone can define a custom gate and a custom synthesis method and write a plugin for it. And this gives people a lot of flexibility with how Qiskit will synthesize different operations in a quantum circuit. And then the pass that does, I'd say the bulk of the translation is the basis translator. So the basis translator has this equivalence library that has a representation of all of the gates that Qiskit knows about, and then an equivalent circuit to translate it to other gates that Qiskit knows about. And we run Dijkstra's algorithm over this giant graph library of all of these relationships to find the path from the operations that are on a qubit in the circuit to the supported operations in the target. And so this is the full library as of 1.3 built in. It's extendable, so if you have custom gates, you can just add to this library. But to zoom in a little bit so you can see what it looks like, you can see here, I'm looking at the relationships from a Hadamard. So if you have a Hadamard gate, you can translate it to SX dagger, S dagger, RY, RX, and so on, and it shows the equivalent circuit on the edge. And so what this pass, the basis translator pass does is it goes through the circuit, finds all of the operations that are not supported on a qubit. We'll run Dijkstra's algorithm to figure out how to translate that to something that is supported on the target, and it will do that for every gate. And it caches it so that you're not doing the search repeatedly and so on to try to make it fast. But what this ends up doing is that naive approach to doing the translation ends up with a very big circuit that can be very inefficient. So you can see here, this is our circuit at the end of the routing stage. And when we translate it, we have this giant inefficient circuit because we're just going piecewise and saying, okay, the definition of this gate in the target would be this. And we dump it out and we have this. And that leads us into the optimization stage. The optimization stage's goal is to try to optimize the circuit, take that giant thing we had at the end of translation and try to make it as compact as possible to reduce the number of operations, to reduce the potential error when we run the circuit on the device. This stage is actually basically a big do-while loop. So we run this block on the bottom here, where we run the bulk of the passes. That is run in a do-while loop until we reach a fixed point. So if we run 2 consecutive iterations and there's no change in the depth or the size of the circuit, we've determined that we've optimized it enough, we can't go any further, and we exit. But we continually run it repeatedly until we do. And one thing to note is we run 2 passes at the beginning, consolidate blocks and unitary synthesis. And this is one of the other differences between level 2 and level 3. In level 3, we run that in the do-while loop. But in level 2, we run it outside. And there's a big trade-off in runtime performance for doing that because the unitary synthesis has some numeric instabilities potentially because of just floating point arithmetic and processors. And so doing it in the do-while loop means we have to account for that, which adds a lot of runtime. So in level 2, we run it outside. In level 3, we run it inside. So let's look at what this does. So if we ran the optimization stage, we have that big circuit from before, and we can condense it down. And this is actually a good example to show the difference between level 2, which is the default in Qiskit 1.3, and level 3. Because if you look at this circuit, by human inspection, I can see some places where we can optimize this. Because if you look in the middle, there are 5 CZ gates, all on the same 2 qubits. And then again, at the end, there are also 5 CZ gates. And that's where that trade-off I was talking about between where you run unitary synthesis comes in. We'll look at how that pass works in a second, but because we only run it once, the transpiler doesn't see the capability of simplifying those sequences of gates, while in level 3 it would because we run it in the do-while loop. So the first optimization pass I wanted to talk about is doing one-qubit unitary p-pole optimization. And this is done with the optimized 1Q gates decomposition pass, which is a real mouthful. And I apologize, I'm terrible at naming things. So when I wrote the pass, I called it that because it made sense to me at the time. And the way this pass works is it looks through the circuit and tries to find sequences of 1-qubit gates all on the same qubit. And it basically simulates those gates to figure out what the unitary is if you were to just compose all of those operations together. And for single qubits, the block sphere is a very nice tool to visualize that. So you can track it as moving the vector between at the end of every single operation to get to its end state, and basically just simplifying it. So you compute that unitary at the very end, and then you just calculate an efficient synthesis of that in the target single qubit gates on that qubit, and you reduce the number of operations to reach that same end state. And so this is very simple, and it's basically all trig and one determinant on a unitary matrix. It's very fast. And we're able to reduce that big sequence, which I did just take out of the output of the basis translator, and reduce it from 7 to 3 operations. But then we can expand that to 2 qubits. So this is where that unitary synthesis I was talking about earlier comes in. So instead of looking for sequences of 1-qubit gates, we can look for blocks on the DAG of 2-qubit gates. So in this example, this is not the example we're looking at. This is an old one that Ali gave me years ago, actually, where you look at the DAG, you look at a circuit representation, you look at the DAG representation, and in the DAG, we're able to efficiently see where there are blocks of operations on the same 2 qubits, while in the circuit, it's a little bit mixed on how it's visualized. So like the DAG lets us efficiently find this, but we look at the DAG and we look for all of these blocks of operations that are on the same 2 qubits that don't interact with other qubits. And then we do the same trick where we simulate it, compute the unitary of that block, and for 2 qubits, that's still reasonably fast, and we have very good synthesis algorithms to synthesize those to other gates. And so we take those 2-qubit blocks that we found in the circuit from the output of the basis translator, we compute the unitary, and we replace those blocks with their unitary matrix representation, and then we resynthesize them to a discrete circuit. And so this lets us greatly reduce the size of that circuit. I mean, you can actually start to see the operations now after running this. And so this ends up being a very powerful optimization technique that does a lot of the work in the transpiler. And then the last pass that I wanted to talk about, which is also one we run in the init stage, is commutative cancellation. So this pass analyzes the circuit to try to find gates that commute. So gates that commute just mean you can reorder them, and it doesn't change the net effect of running those 2 gates. So you can flip the order, and the output state is the same. And it looks for those relationships, and if it finds them, it tries doing that. And if it does it, are there any opportunities to do an inverse pair cancellation? So in this simple example on the right, if you had a circuit that looked like this, where you have a CX, a Z, and a CX, you could commute the CX or the Z on either side of the CX. And if you did that, then you'd have a CX pair that was a self-inverse, and you could cancel it, and then reduce what was 2 2-qubit operations to 0. And so we run this in the optimization loop, and it finds a lot of opportunities to cancel lots of gates. And at least historically, in old versions of Qiskit, we spent the most time doing this. In 1.3, it's actually significantly faster. And then that leads us to our last stage, the scheduling stage. And the scheduling stage is, okay, we've now mapped our circuit, translated it, optimized it, so we have something that should produce good results on the device. But there are some times where you need to account for the timing of the circuit. The best example is dynamical decoupling, which Peter will talk about later today. But if you need to account for the timing, that's where the scheduling stage comes in. And the scheduling stage just looks over the target. The target has the runtime of all of these operations, and it tries to find all of the idle periods in the circuit where you have time where qubits are not doing anything. And it tries to account for that with an explicit operation. By default, there are 2 options that you can opt into. There are different plugins for the scheduling stage. For ALAP scheduling and ASAP scheduling, just as late as possible and as soon as possible. And all this pass does is just looks for those idle periods and inserts a delay operation, which is an explicit operation, and it inserts that to account for the time based on the runtimes returned in the target. So if we look at the output of this, I believe I ran this with as late as possible scheduling. You can see that it inserts, the only difference between these is that it inserts delays. So if people have really good eyes, especially in the back, because I doubt you can read any of the text here, there are extra operations that say delay, and it says how many time units it spent on that delay to just account for the runtime. But there are more advanced error suppression techniques that you can leverage this timing to further improve the fidelity of the circuit when you run it. So the last thing I wanted to talk about very briefly is we've gone through all of the work that the transpiler is doing, but the last several months, the Qiskit development focus has been on improving the performance in the transpiler, and specifically in the 1.3 release, which is coming out next week. The performance is significantly improved. So as was talked about yesterday when Heather was talking about Qiskit performance, the 1.3 release, we ran the bench press benchmarking suite that Heather was talking about, and the 1.3 release is way faster, like 5 times faster. So just to give a high-level view of that, when we ran bench press with 1.2.4, which is the most recent stable release, it took over 6 hours to run bench press. With 1.30 RC1, it took slightly over an hour. So we saved 5 hours to run this benchmark suite. If you compare that to TCAT, when we ran Qiskit 1.2 versus TCAT 1.31, which was the latest release of TCAT at the time, Qiskit was 13 times faster. When we compare 1.30 RC1 against TCAT 1.34, which is now their most recent release, Qiskit is 58 times faster, and still reducing the gate count about the same amount, about 20%. And Qiskit 1.3 is, on average, 5 times faster than Qiskit 1.2. And so I graphed that showing, comparing the same benchmark suite, bench press, and comparing the results of 1.2.4 against 1.3.0 in 2 different ways. The left is showing just the ratio of the runtimes for each individual benchmark, and the right is graphing them on a scatter plot where the y-axis is 1.2.4's runtime, and the x-axis is 1.3.0's runtime. And you can see pretty clearly there's a trend that it's faster across the board, on average 5 times, sometimes more, sometimes a little less, but averages out to about 5 times faster. And this is, at least for me, very rewarding because I spend a lot of time working on performance, and I remember back, I don't know, maybe 5 years ago when the Hummingbird devices were coming out with 53 qubits, we were trying to do transpilations at 50 qubits, and it was taking minutes to an hour, and getting to the point where we're this fast with these giant circuits is really rewarding to me. So that's all I had to talk about the Qiskit transpiler. I think the next speaker is David, who's going to be talking about the Qiskit transpiler service. So I'll hand it off to him.